All right, good morning. So welcome to the start of week 7. Quiz 1 is coming up this Wednesday, and we will have that triple room set up. So do take a look at where you're supposed to be for Wednesday. So by a show of hands, how many of you would say that you're still just a little bit uncomfortable or a lot bit uncomfortable with pointers? Okay. That's good. That's good. Okay, so that's good that you're so candid, actually. So let's do this. Before we take a look at some trees some more, a couple of announcements, and then let's take a look at some pointers for a moment. So 1, go find those pictures for problem set 4 if you want dinner on us. 2, hacker section is in the virtual terminal room tonight as opposed to the cafe in Maxwell Dorkin at 7 p.m. And finally, the quiz 1 on Wednesday. Any questions related to any of that kind of stuff? Now, the competition so far is going pretty well. We've gotten a few dozen photographs thus far from a few different sections, and no one has come close to finding all of them. So if you've not yet dived into that project, do go for a stroll with a friend or two from your section and see if you can't dig up some of those photos. Yeah? Is there a pass-fail deadline in the sense of changing your status? So I think it passed for the university, yes? Okay, so yes, it passed. So hang in there. Come chat with me if you want to talk about things. Other questions? Okay, so let's go ahead and do this. So I'm going to set up a little template, as we often do, for a bit of a program here. Int argc, char star argv. And let's go ahead and do this. And I'm actually going to employ GDB, which by another show of hands, how many of you have actually been using GDB? All right, so that's quite good too, since it is a wonderful and increasingly useful tool, especially in the context of pointers. So let's go ahead and do this. Let's come up with a completely arbitrary program, but that's nonetheless illustrative of some of these fundamentals that will certainly be assumed for quiz 1, but more importantly than that, are certainly useful in the problem sets to come. So let's go ahead and declare a couple of ints. Call this x equals 6. Another one equals y equals 7, just so that we have something to play with. Actually, let's just stick with 1 for now. So if I want to start dealing with pointers, let's talk about what's actually going on here. So right now, in the state of my world, my program, when I run this thing, is going to look roughly like this, with main so-called what down here? So this is the so-called stack frame, right? And inside this frame, and this is RAM, this whole thing, is just a bunch of memory that's allocated for all of main's what? Give me something. All of main's okay, I'm not even sure what that was. So local variables, and also its parameters. Recall the parameters to main include argc and argv, and also any of these local variables. So somewhere in main stack frame, the moment I've declared this variable, are 32 bits that are henceforth to be referred to as x, and currently stored in that chunk of memory is going to be the value 6. All right, so that's a pretty simple picture to paint, and we've been playing with that kind of stuff for a while. If I now want to declare a pointer, though, the syntax for declaring a pointer called p is going to be what? Star p. All right? And specifically, this is a pointer to an integer. So all pointers, no matter what they point to, remember, are 32 bits. So a pointer is, in that sense, a sort of data type unto itself. But it's not quite a data type in the same sense as an int and a char, because it is, in fact, always 32 bits, but it can point to different things. Now, if I want to depict this in this picture, somewhere in main's frame, it might be next to this variable, it might be elsewhere, we don't so much have control over that. There's going to be another 32 bits allocated. Henceforth, they're going to be referred to as p. And at this moment, what's going to be stored in this 32-bit value? So, I mean, right now, technically an address eventually, but right now, who knows, right? Maybe it's 0 by default, depending on how the computer has laid out RAM by default, but who knows? For now, it's just a question mark. But if I instead change this value to say that, you know what I want to store in p by default? Just arbitrarily, I want to store the address of the variable called 6. Well, how do I go about expressing that in code? Say again? So this is where we have the ampersand, which is just the address of operator. And if I want to store the address of x, you quite literally translate that to address of operator x. Now realize that this is equivalent to 2 lines of code. So this also equals saying int p and then saying down here, p gets what? Right, ampersand x. So don't think that you have to put the p again. The understandable confusion in these two approaches, I think, is that up here you sort of have the star and the ampersand in the same line, but down here it's being split and you don't repeat that star there. But again, remember what these things mean. When the star is on the left-hand side of an expression like this, that typically means that you're declaring it to be a type, a pointer to an int in this case. If though you're simply doing an assignment and you just want to put in a pointer the address of something, you simply say p gets address of x. So now at this point, what goes in this box where formerly there was just a question mark? So a pointer to x. And typically we've started getting a little casual and we express that by drawing an arrow, which conceptually might look like this. But technically, if we want to be anal about what's really going on here, what really could I be writing in this box rather than waving my hand and just drawing an arrow instead? So what goes in this box? So a hexadecimal, but even that was sort of an aesthetic detail. It can be any type of number, but specifically what number? Sorry? So whatever ampersand x is. And at this point, it's not clear because I've been abstracting away. But if we start numbering all of the bytes in this frame, so this is byte 0, this is 1, this is 2, this is 3, and so forth, maybe this is byte 234, and maybe this one is 238 if they just so happen to be next to each other in memory. And so what now goes in this box is 234. So that's all that's going on. And again, I think you think about this either way, either in terms of what value is getting stored in here or abstract away as just an arrow, because for the most part that tends to suffice, but at least appreciate exactly what's going on with this otherwise cryptic syntax. Well, now let's go ahead and do a couple sanity checks. So let's go ahead and print out in hexadecimal, just arbitrarily. We could do this in any base system. Let's go ahead and print out the value x. When I execute that line of code, what obviously should be printed? All right, so just 6. So I'm going to go ahead and make pointers. I'm going to go ahead and redeclaration. Let me get rid of that. So let me go ahead and compile this. It's complaining about an unused variable p, and that's fine for now because I'm not actually doing anything with it. And now indeed we see the value x. Now let's take this one step further. Let's go ahead and print out not x, but the address of x. All right, let's recompile this, rerun pointers. And now I get this cryptic looking string. It isn't hexadecimal, but that's arbitrary. If I wanted to, I could have just said print these both in decimal. And now I get this value. And it's a negative value, which that seems a little strange. What's going on? Why is it showing up as negative? So it's interpreting the value as signed because remember that a pointer is 32 bits. So in theory, it could be using that leftmost bit, which often signifies negativity. But that doesn't make sense, presumably in a block of RAM, where if you start counting at 0, in theory, you should be able to count up to how many bytes? Sorry? 2 to the 32, so roughly 4 billion. So in theory, what's the maximum amount of RAM that one program could use, just based on that intuition? 4 gigs, right? So that's sort of the rule of thumb. And that's not necessarily the case. The operating system can dictate far less. But in theory, that's the total amount of memory that you could actually address within your program. So if I actually wanted to see what this value really is, I could instead just specify that, you know what, this should actually be shown as an unsigned int. Let's recompile this and show it. And what's going on here? Sorry? What's going on here? That's stupid detail. All right, it's just the formatting string. OK? All right, so don't get hung up on that. So let's go ahead and do this now. If I want to go back to the state of the world a moment ago, where remember that I was printing things out in hexadecimal, what line of code would be equivalent to this if I now want to involve this pointer that I declared earlier? The goal is to print out in this third line the address of x, but using the pointer notation. All right, yeah, just p, right? Pretty straightforward. If a pointer is just an address, and we already put the address of x in there, we run and compile this thing, we should see exactly the same thing. What if I now do a fourth line where I bring back this star? Now notice that in this context, the star is different from the star that was up here on the left-hand side of the declaration. What does it mean here to say star p? Sorry? dereference operator, right? So different nomenclature, same symbol, but what this means is that go to the address that's in P. Don't show the address, go to that address, which in this case is this value. So what should get printed in this fourth line? Yeah, so 6. So now we have that. Okay, again, silly example, but hopefully if you understand these basic steps, the rest sort of follows from these basic definitions. But just so we push the envelope a little bit now, what if I do something a little crazy and say int star star pp for pointer to a pointer equals, what do I want to do here? What if I say this? So logically, is this a reasonable thing to do? To declare a pointer called double p and store in it the address of a pointer itself. Well, what's going on conceptually? Let's put another box. It's going to be 32 bits because it's still a pointer. This thing's going to be called double p. And then stored in here, according to that line, should be what? OK, so 230, yep, sorry, handwriting. 238, which was the address of the pointer. So first of all, yes, that is syntactically valid. You can have pointers to pointers. And in fact, you guys have been using them for several weeks, perhaps unbeknownst to you, but we'll see that in a moment. If I now go ahead and run this code after changing this to be double p down here, to be clear, what's this blinking line going to represent when printed? The address of what? P itself. So let's make this. And obviously, we're not going to see the same value since I chose my numbers arbitrarily. All right, so now there's this weird error here. So now, because we're trying to print as hexadecimal these various things like pointers as opposed to true ints, we can at least start casting this stuff and say unsigned int. And over here, we can say we can say, what was this thing? Unsigned int. Let's go ahead and recompile that. Let's see, 13 and 14. Still complaining about these. So I'm just going to forcibly say that these are unsigned ints because otherwise the compiler is going to keep complaining that I'm trying to print as an int something that's actually a pointer, right? Slightly different concepts. All right, so that's just to get rid of warnings. It's not going to change the behavior. Let's run this program again. All right, so now notice that this address is the same as this, and that was expected as before, but this guy's a little different because that's actually the address of that variable. Let's push a little harder. If I now go here, and again, even though this is looking ugly, again, it all boils down to these basic principles. What's this last line going to print now? Star double p. So not 6, not 6. It's going to print the address of x, right? It's going to, this is equivalent to what syntax? The value of p itself, or address of x, which is equivalent to that in turn. And if you've gotten lost here, at least maybe make a note to yourself as to which of these is equivalent to which. And I'll make this code available online later. But let's go ahead and run this now. And in fact, this new line of code is still the same as this one, which was just p, aka the address of x. Now let's push a little harder, and if we want to go one step further, let's actually, so this is going to look a little cryptic, and don't worry if you don't quite follow this last line. Let's go ahead and say that this is, let's see if we can get away with this. All right, so this is, OK, let's give this a try and see if the compiler likes this. OK, so star pp should give 6. All right, so we've sort of undone all of the work we just did. But it illustrates, hopefully, if you, at least you were able to follow those several steps, that at the end of the day, these pointers, I mean, it's just the address of this, or maybe the address of that. But effectively, the star operator versus the address of operator just sort of reverse the effects of each other. And what's really going on underneath the hood is this kind of stuff. OK, so that's pointers in a nutshell. And in fairness, I will say, and I don't know why this is the case, but to this day, I actually still remember being in the Elliott House dining hall, sitting down with my TF in 1997 or 8. It was in the corner. There was a big round table that's apparently no longer there. And again, useless details that I, for some reason, remember. But that was the day that I finally got pointers, which is only to say, if you guys are still struggling or at least uncomfortable with some of this stuff, frankly, pointers are perhaps the most sophisticated or arcane feature of C, certainly that we look at in this course, and that's totally to be expected. And know that you were introduced by way of problem set 4 to a bit more about pointers, using those file stars and passing around buffers and so forth. But know also that in problem sets 5 and 6, will you actually get your hands even dirtier with pointers. And frankly, I think just with additional practice will come greater savvy. So, yeah. So the double star in the blinking line or the one up above? Above. So this one up here? OK, so on the left-hand side, what this is doing, these 6 characters that I've just highlighted in, let's say, what's going on with these 6 characters is that is declaring a pointer to an int. OK? It similarly is the one above it declaring a pointer to an int. And now I promise that you've actually seen pointers to pointers before. And it turns out that every time we've been writing argv bracket notation, well, recall what an array really is. An array is effectively what? Or the name of an array really represents what? A pointer to the first element. So really, all this time, and some textbooks and online examples certainly do this, we could have been writing that instead, which is actually equivalent. Because in a nutshell, all that's going on underneath the hood with this thing called argv is that when main is actually called, when your program's run by default, you get, obviously, this 32-bit chunk of memory called argc. And all of this is going to be, for the most part, in main's stack frame. But you also get this array of pointers, each of which points to a string. Potentially something like a dot, I have to make room, o, have to make much more room. Can't quite spell when drawing squares. A dot o u t backslash o. So when you have your program being run, so argc is just this int. Argv, in turn, you've always known is an array of char stars. Well, that makes sense, because if each of these things is a char star, that's just a pointer to a char, which is equivalent conceptually to what we've been calling what? A string. So if you run a.out, you have that. If you write the word foo after a.out at the command line, what you get is foo \0, which is somewhere in memory, and its value its address just gets tucked away here. But if an array of char, if argv is an array of char stars, well, and an array is really just the address of the first thing in an array, what argv really is that. OK, we draw it, as I did, as an array. But if we really draw argv as this declaration suggests, a pointer to a pointer, is this not the better picture? Argv is now a 32-bit value that's pointing to this square here. But what's this square? A pointer to the actual string. OK, so one step further. Don't worry for Wednesday if you quite followed that part there, only because pointers to pointers are something we'll look back at, look more at perhaps with problem set 5 and or 6. But just at least appreciate that it all boils down to those basic principles, the address of or the dereference of something. Questions? Yeah?
You said that the asterisk, when you're declaring the variables, isn't the same as the address of operator later.
OK.
So why don't you put space between the asterisk and the variable name?
The asterisk, oh, so like down here?
Could be like int style space.
So like I just did? So this is just a stylistic thing, and most people tend to put, when you're declaring a pointer, most people put the star right before the variable name. And frankly, this is just a random aside. I got in the habit early on in the semester of always writing the function declarations like that, and I just stayed with that, although most people would actually write it like that. But the difference is immaterial. You can have that white space there. It's just a stylistic thing. I would just be consistent. Other questions? No? Okay, so if still a little puzzled as to pointers and such, that's fine. Strike up a conversation with us, but at least remember that it ultimately should boil down to some of those basic principles. All right, so trees, and this is something that will recur in problem set 6. When you actually implement your own compression algorithm, conceptually you're pretty straightforward. You have the root of a tree. It's sort of like a family tree in that sense, and then it has 0 or more children, each of whom can have 0 or more children. Trees, for our purposes today, are interesting in that we can use them to solve problems that we previously might have had to solve less efficiently, or at least with less sophisticated means. So consider this example of a tree. A tree, again, is defined by its root, much like a linked list is defined by a pointer to the first element, at least in our implementation. So if we wanted to represent these numbers here in a so-called binary search tree, we're going to need some kind of data structure for each of these nodes, which is here drawn as a circle. So if I wanted to declare a data type that's going to let me implement this thing in memory, what data member should I give this data structure that I'll arbitrarily call a node? What has to be inside of each of those circles when we translate it to C? Yeah? So 2 children nodes. So right, the 2 arrows for each of these nodes, or the maximum of 2 arrows, seems to suggest that we need to remember those 2 more nodes. And what else needs to be tucked away in each node, as the picture suggests? So an actual value. So I'll do that one first, and I'll say that inside of this thing is going to be an int n, but we could call it whatever we want. And now the arrows are something that we can actually mimic pretty effectively. Anytime we've seen arrows, we're usually talking about pointers, because we probably don't want to store the actual children nodes in the node, because you have this sort of circular problem. Then if each of those nodes has a child or 2, then you have nodes within nodes within nodes. I mean, very quickly, it's sort of hard to imagine what that data structure looks like. It very quickly seems to get bloated conceptually. But rather, we can take that linked list approach. We don't want to necessarily store the children nodes in the node, but what could we store instead to mimic that arrow idea? So we could just store pointers to these things, all right? And remember that if you want to have self-referential pointers inside, much like we did in our linked list, we actually need to say something like struct underscore node up here, though that name is arbitrary. And then in here, we can say struct underscore node. And then I'll go ahead and call this left so that it's a pointer to one of those data types. And then I'm going to have one more, which is almost identically declared. Star right, close the squiggly, and then this thing will be called a node. Okay? So that might be a very reasonable definition of a node in the language known as C for a node in a binary search tree. Agree? Disagree? Anything wrong? All right, it's pretty much identical to what we did for a linked list, except that rather than having one next pointer, it's obviously got these 2 pointers. Now, just to do a sanity check, it looks like some of the nodes in this tree are not going to have children. Is that problematic for this definition? No, I'm saying no. Why? What can we do to mitigate that potential worry? You just call them null, right? Just terminate the end of the tree by just setting these things in your own code to null. All right, question in back? Yes? No? OK, so let's assume now that we have this thing defined in our program, and we also have the workings of a program. And assume that we whipped up something already like we did last week called list1 or list2, whose purpose in life is to create this kind of tree in memory. Just like our linked list example remembered where that linked list is by declaring a pointer called first to the first element, what might I use in my program to actually represent the root, so to speak, of a binary search tree like this, given this definition of each node? What global variable might I want to define in that kind of program? It's a one-liner. We'll call it root, so I'll give you that hint. So what should root be defined as a global variable in this imaginary program? Yeah, so just a node star, right? And again, we're just stealing ideas from our previous implementation of a linked list, right? Because even though that thing's pretty big and it's got, what, 4, 5, 6, 7 different nodes, the only one you need to remember the address of, obviously, is the first. Because from the first can you reach all the others. And the same was true for our linked list. All right, so at this point in the story, are you comfortable with the fact that this effectively can represent a thing called a binary search tree, which looks like that, each of whose nodes are implemented in C like this. Same page? Yeah, question.
When you call it node star, would we presumably do some sort of type definition node to be that structure?
So we have assumed that this is a node. So even though I called it struct underscore node here, the only reason I did that is because I needed this self-referencing within the definition. But because I ended this declaration with the word node followed by semicolon, that means this whole thing is called a node, which means a node star is just a pointer to one of those things. And that's as simple as you can make this definition. You can't get rid of the star if you actually want to have a pointer to the thing.
So even though the node is outside of the curly, it still defines the whole structure that you just.
Exactly. This is just the way you do it with a type def and a struct. And we did exactly the same thing with our linked list examples. So you just have to memorize what the syntax is. A question in back? OK, so now let's do something with this. And again, this is sort of a building block that will recur when it comes time to do problem set 6, which, again, will be about compression, for which we'll use a tree. But let's go ahead and do the following. Let's actually implement a function called find, whose sole purpose in life is to find a value in the so-called binary search tree. But it's at this point in the story where we need to actually refine our definition of this thing. Beyond just looking like this thing, there's actually a pattern to the numbers that are in this data structure. What appears to be the pattern or the assumption we can make about a binary search tree. Because to be clear, this thing was not just called a binary tree, bi meaning two, so 2 children maximally each, but it's a binary search tree. What does that appear to suggest about all those numbers? So they're sorted in a sense. What does it mean to be sorted in a tree? Let's refine that definition. OK, so based on the numbers I've chosen, you essentially have as the root node, as the parent node rather, a median of the 2 children nodes. But we can generalize further. A binary search tree simply says that a node's left child is less than its value, and its right child is greater than it. And that in and of itself is sort of a recursive definition, because notice that 33 is less than 55, but 77 is greater than 55. Now look at the bottom left of the tree. So 22 is less than 33, but 44 is greater than 33. So that's simply the pattern that follows. So the binary search tree is defined as that, with each of the children having that relationship to each of their parents. So now let's go ahead and implement this function that is simply going to return true or false whether or not some value n is actually in this tree. The global variable that we have access to, much like we did in our linked list example last week, was that thing, and I'll rewrite it here, called root. So if I want to start searching this tree, much like I started searching a linked list, I can begin with the root. All right, so what can I do here? How can I go about starting from the root and looking for some value? Yeah?
Compare the value that you have to the value in the node, and if it's less than that, you go left. If it's greater than that, you go right.
Good, good, right? That's actually quite similar in spirit to some algorithm we saw a while back, right? If we start at the root node, check its value, and if the number n we're looking for is less than that, obviously we want to take a left and go down the left branch, so to speak. If instead n is greater than 55, we want to take a right and go down the right branch. But what's the case when we go one level deeper in the tree? Does the algorithm change at all at that point? Oh, it's the same idea. We've sort of divided the problem and have conquered one step at a time, either the left branch or the right branch, which makes this algorithm that we're developing verbally for binary search trees, or BSTs, identical pretty much to what? Just binary search when we just had an array. So it's a little more interesting now that we've got these pointers involved in this explicit tree structure, but the algorithm conceptually is the same. And here's one of our first clever uses, or useful, particularly compelling uses for that concept known as recursion. So we've dabbled in that thus far, and you'll come back to that likely in problem set 6 when we do begin manipulating trees. But for now, I'm going to go ahead and lead us a little bit and say this: return recurse on, let's go ahead and say root n. And there are different ways to do this. But I'm going to claim that implementing find is as simple as calling some other function that I'm going to call recurse, and I'm going to pass to recurse the root of the tree and the value n. Okay, so this is sort of kickstarting this process of searching this tree. So the question now is, what should we declare? Well, that was embarrassing. What should we declare recurse as? Well, let's take a look. We'll write it over here. So recurse's sole purpose in life is to implement the algorithm that Tomo just suggested, which is to start at the root and then either go left or go right and then repeat. So here's this function. So this too is going to return a bool. It's going to go ahead and be called recurse. It's going to take as its parameters a node called arbitrarily ptr and an int called n. All right, turns out this function can be implemented pretty quickly. Well, what do we need to do here? So in any recursive function, there's two kinds of cases. What did we generalize those things as? Base case and the so-called recursive case, where you actually call yourself. Well, what's the base case going to be here? Sorry, I hear some murmurings. So if the node equals n, okay, so if the value in the current node equals n, we can immediately return true, but we actually have to be careful here. So what do we need to be careful about? So there is this null check, right? So we should probably have, so if pointer equals null, just in case, maybe there is no tree yet. Maybe root itself is null. What should we return if pointer is null? All right, so obviously let's just return false. So return false. And to save space here, I'm going to write everything on one line, but that's syntactically valid if atypical. All right, what's the other check? Well, if it's not null, we can do else if, and now I want to check if n equals the current node's value. How do I express that syntactically? What do I write? To check the current node, aka pointer's n value. Yeah, so pointer arrow, which says follow the pointer and go into its data member called n. If I find that n equals pointer n's value, what do I want to do? Right, so I can return true. Sorry, I should have written false in uppercase to be consistent with our library. Okay, and now, so it appears actually that you can have in recursive functions two base cases. And we actually did see that in our Fibonacci implementation, two base cases, where you sort of hard code the answer. But if it's not the case that pointer is null, but rather it is a node, but its node's value is not equal to n, what must we now do? So we have to call ourselves recursively, and that implies I'm going to have to call recurse again, passing it a pointer and the same value n. But what pointer? The right or left. So how do I decide which to call? Sorry? So if it's bigger or smaller than the current value, so actually I can copy and paste most of this code. So else if n is less than ptr arrow n. So if n is to the left of this node, I actually want to return not a hard-coded value of false or true, but what do I want to return? The result of calling myself on my left child passing in the same value of n. Okay, and let's round this out with just one last statement and then ask what that exactly means. Do I need another else if, or can I get away with else here? Else is fine, right? There's really only three cases. It's equal, it's less than, or it's greater than. So I'll just write else. So else, I'm going to return that same statement as before. So return recurse ptr, and to be clear, for those barely following along, what's here? Right. OK. All right. So why does this work? So at this point in the story, remember that we began up here. So we called find and passed it n. I wanted to search this data structure known as a binary search tree recursively, which is addressed by way of that variable called root. Sorry? missing the... What? Okay, sorry. When I call the function. Oh, the end. Thank you. See, if you speak to me slowly, I catch on eventually. All right. So there. So I'm passing in now n. Thank you. All right. So at that point in the story, we decided to solve this problem recursively by sort of dividing and conquering the problem of all those different nodes. So I called this helper function, so to speak, called recurse. There are other ways to do this, to be sure. And I passed in the root of the tree, which might be null if there's no tree, but that's fine. We check for it, and the value n. Now here's my actual function called recurse, whose sole purpose in life is to perform 4 checks maximally. If pointer is null, clearly the value's not in the tree because we haven't found it yet. And granted, this statement, when we wrote it first, might not have been obvious, say, to the developer writing this kind of code for the first time. And frankly, one might be inclined to write these lines of code first, just conceptually. They're more clear. And that's fine. We sort of had the foresight to put this thing here in advance. But you get better at this sort of thing. So if pointer is null, obviously the value is not in the tree. Return false. If the thing is not null and n happens to equal this node's value, obviously return true. Otherwise, we've got a decision to make. Do we check to the left? Or do we check to the right? Well, the interesting takeaways from this line, I would say, are at least twofold. One, the means by which we check, again, the value of a node that's being pointed to by some pointer, PTR in this case, is this syntax, PTR arrow n, just like we saw there. But the only bit of conceptual trickery now is this thing. Not only are we recursing, we're also returning recursing. So why are we doing this? Well, at this point in the story, when recurse is first called, this thing too returns a bool. And in fact, I returned a bool up there by calling return recurse, right? Because I just keep passing the buck effectively. I myself recurse at this point in the story. I don't know what the answer is if I actually have to keep searching to the left or right. So I'm not going to return a value per se. I'm not going to return true or false. I'm going to let someone else return the answer for me or compute the answer for me. Just so happens that guy is me, just being invoked again, but I'm just going to return the answer from this invocation. And he too might keep passing the buck again and again and again, but eventually one of these recursive calls will bottom out, so to speak, and will actually return a hard-coded true or false. Why? Because of these base cases, right? That's the sort of magic. Right? And let's consider just a trivial example now. If our tree has just one node and thus looks like this, and root is declared as a 32-bit pointer, which by nature points to that node, and this data structure is just one of those structs that we defined earlier. So what happens? Well, we call find on, say, the value 54. Okay? I return the recursion on passing the root pointer and the number 54. Now I'm in this function. So here, is pointer equal to null? No. Is n equal to n value in this node? No. Is n less than n in the current node? That's true, because the root is 55. I'm looking for 54. So I'm going to return the result of calling recurse on pointer's left child, passing again 54. Well, what is this already at this point in the story? So it is null. So yes, the function does get called, but immediately that second invocation of recurse returns instantly, but returns false. So now at this point in the story, and I'll erase this to be clear, what effectively has just happened the moment this function is done executing is that now floating around in memory is this value. So it's sort of like a copy. It returns a value which is effectively the same as changing what's actually there conceptually. And so what gets returned is false, which is in fact consistent with what the story should have told us. So the neat takeaways here are, one, pointers are actually getting useful in an interesting way, rather than doing these silly little examples where we just, play around with syntax, which is not by any means compelling. But moreover, recursion finally seems to have some interesting applications, right? It's a strange thing to introduce recursion often in these intro classes, because clearly implementing Fibonacci recursively was Pretty stupid, right? We had that ridiculous poor performance, and so that's why we introduced memoization and essentially caching and those kinds of ideas related to dynamic programming. It's nice because that's a bite-sized problem. It's kind of scarier to introduce tree recursion the first day someone's seen recursion. But finally now, hopefully you're convinced that there's a hint of some neat functionality here, and quite likely you'll use that in your own problem sets 6. So a quick reminder that tries were introduced last week too, and this is another type of tree structure, certainly much more complicated, if you will, than a typical tree or a binary search tree. But what was the motivation, just to recall, for introducing tries coming on the heels of hash tables? I mean, who cares is the question at hand here. Yeah? Right, so recall that the goal here was to look up strings in that story we told on Friday. And a hash table can look up a string pretty efficiently, but because you might get those chains, so to speak, in memory, what did we say the running time was of a hash operation and a hash table implemented with those chained lists? I mean, it's big O of n, and I kind of cheated. I said, well, if you sort of make sure that all of your chains are the same length and you have m different chains, it's sort of like saying big O of n over m. But if m is a constant, it's still big O of n, right? It's still linear. But a try, recall, takes how many steps to look up, say, a 4-letter word? 4. Well, what if there are 200,000 words in the try? How many steps does it take to look up a 4-letter word? 4. So that's compelling. But there's a price you pay, and the picture itself almost begins to hint at the price you pay. What was the trade-off for using a try? What do you have to spend in order to get that higher time performance in theory? So you need more space. You need more memory, right? Each of these things, even though for pictorial reasons they're just chopped off just so that you see little pieces of them, each of those things is an array of size 26. So this data structure is actually very wide. It's very dense with a lot of memory, many of whose cells might actually be empty. There might not actually be any valid data there. So a try is one of the data structures we'll put forth, particularly for the for problem set 5 when it comes time to implementing a data structure for those of you perhaps a bit more comfortable with such. But we'll conclude today with this one look at one other data structure that's at the end of the day a tree, but it's interesting in that it also allows us to solve a problem in a more interesting way than we were able to in the past. So quick piece of definition. A heap, henceforth, is just a binary search tree, but it's got 2 additional features. It is complete. So what does that mean? Well, that just means that if you start drawing this tree, all of the nodes are as far over to the left and as high up in the tree as possible. That is, any holes, so to speak, pictorially in the tree are only at the bottom right of the tree. You don't have random leaves, so to speak, missing in the middle of the tree or on the left-hand side. Okay, with that said, in informal terms, there's this last property. It's called the so-called heap order property. So a heap is, again, just a binary tree, a binary search tree. But there's this, is a binary tree that satisfies the heap order property, which simply means that each node value is greater than or equal to that of each of its children. Okay, and actually, this is misleading. This word should not be there. So the heap order property is different from the search property. So it's a binary tree that has this heap order property, whereby, again, each node's value is greater than or equal to its children. So if you take an arbitrary node, you can trust that it's bigger than its children, and really, by extension, all of its descendants. So with that said, here's 3 samples. The thing on the left, the far left here with the blank line underneath it, is that a heap? Yes or no? Okay, sure. Okay, I could have said that. So sure. So 1, does it satisfy completeness? So where's the only hole conceptually in this tree? Well, the bottom right, so that's OK. Everything's as far to the left and as high up as possible. Does it satisfy heap order? Well, take a look at each of the nodes. Does any of them have a child that's greater than it, or a descendant that's greater? No. So that, in fact, is a heap. Thing in the middle is not a heap. Why? It's not complete, right? The nodes are not tucked away in the top left, so to speak. Thing on the far right, heap or no? No, why? Good. So we have 8 is greater than 6, which means a child is greater than its parent, which violates that so-called heap order property. All right, so now the question, who cares? Well, it turns out that you can use heaps and you can use these properties to actually begin sorting more efficiently than we could have perhaps with just arrays at our disposal. So recall a while back we looked at selection sort and bubble sort, and we talked briefly about insertion sort, also looked at merge sort, and each of those had some ups and downs either in terms of time or space. Now that we finally have more interesting data structures at our disposal, can we solve those same problems but perhaps better? So a quick piece of terminology, heapifying and almost heap. So silly jargon, but you will see it used. To heapify an almost heap means to take something that, frankly, is almost a heap and turn it into a heap. So on the left-hand side, why is that thing almost a heap? What's wrong? So 9 is greater than 2, and yet it's below 2. So you might guess that the simplest way to fix this thing is just to swap 9 and 2. And that seems to solve that problem. Yes? No? No, so there's still another step here because now 5 is greater than 2. So now on the right-hand side, 5 is still out of place. But this principle of swapping nodes, if we apply it again and again, can actually let us take an arbitrary binary complete tree and turn it into a so-called heap, which is useful. So a few scary steps, but all of which individually are pretty straightforward. Consider the following example. The goal at hand is to sort, or is to heapify an arbitrary binary tree. I just want to turn this thing into a heap. On the far left, is this thing currently a heap? No, it's kind of a mess, right? Because if 1 is the root node, but everything below it is bigger, that already violates the heap order property. Moreover, down here, notice that 7 is below 2, and that's bad. So there's a lot of problems with this thing. But what this slide suggests is that very algorithmically, very carefully, can we iterate through this tree and fix all of those problems. And the means by which we do this is as follows. If we start by considering the bottommost rightmost subtree, so the smallest tree of size 3, as far down in the tree as possible, that gives us those 3 nodes, 2, 7, and 6. Okay, so the smallest 3-node tree as far down in the tree as possible is where I'm looking. What does it take to heapify that little trio of 2, 7, 6? What needs to be swapped with what? All right, so I can just swap 7 and 2. Swapping 6 and 2 would partially fix the problem, but I would then need to do what? 7 and 6, which is just stupid. Let's do half as many steps and just swap 7 and 2. So that brings us now to the second phase. So now I have just heapified, so to speak, this subtree, so to speak. Now what's next? Well, I'm going to move up in the tree. So I'm going essentially from the bottom right corner, left, 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 up, left, 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 up, left, left, left. So the next tree to consider is that 3-node tree involving 8, 9, 3. So what's wrong with 8, 9, 3? To be clear, in the second picture here, in the top middle of this slide. What's wrong with 8, 9, 3? Okay, 9's obviously out of order. So we want to swap 9 and 8. That then yields this picture here. So in these dashed lines now is the correct picture. Now we move, as I said, left, 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 left. So the next tree that sort of gets swallowed up by this algorithm is that 5-node tree involving 5, 7, 4, 2, and 6. What's wrong with that tree? So 7 is out of order, right? 7 should be on top of 5, right? So we need to fix that. And then anything else? Then 6 needs to be on top of 5 as well. So it seems we need 2 swaps. So we need to sort of percolate through the whole tree top to bottom. But at the end of the day, now if we look at this subtree and we swap 7 with 5 and then 6 with 5, we then get this result down here. All right, now we're as far left in the tree as possible. So now we shift up and to the right, and we start going again, which just means we have 1 tree left, the whole tree itself. At this point, in the bottom left picture here, we still have some heapification to do because 7 and 1 are out of order and so forth. So if we fix this, swapping which? What do I swap in this whole picture here first, starting at the root? So 9 and 1 get swapped, all right, and that fixes that problem. But now we have 1 here, wherever the cursor is, 1 and 8 need to get swapped as well. So at the end of this very long story, which actually can be implemented fairly straightforwardly in code, I'm not going to do that today, you can actually get this resulting binary tree, which is still complete because we didn't add any arrows. We left all the arrows intact. We just swapped values, but it's also now satisfying the heap order property. All right, so now, who cares? All right, so what was the point of this whole exercise? Well, how many steps did it take to heapify this whole arbitrary tree if it had n nodes? How many steps did this whole process take? Well, let's think about it. Essentially, because this tree is complete, how tall is a tree with n nodes, given that it's a binary tree? So it's log base 2 of n. So already the height of this tree is log 2 of n. So that means that the total number of times that we can move up in this tree is log of n. Okay, so that's the height of the tree, how many steps we can go upward. The question then is, how many times do we have to consider these subtrees? Well, how many different subtrees are there? Well, I kind of simplified things. Early on, I said start with a subtree of size 3. But really, I could have started with a subtree of size 1, because what does it take to heapify the tree containing 6? Nothing. Then I could have tried this one. Done. Now I move on to this one. Done. Next I move on to these nodes and so forth. In effect, even though we simplified some of the steps to keep the process simple, you can effectively consider each node in the tree as a possible root of one of these subtrees. Right? Conceptually, that's all I was doing, sort of moving through the tree using a different root node for each subtree at once. So how many such candidates are there for root nodes of these subtrees? N, and actually thinking now about the height of each of these subtrees. If the whole tree is of height log n, what's the maximum height of any of these subtrees? Right, it's still log n, right? That might be generous, but it's still no more than log n. So that means we're considering maximally n different subtrees, each of whose heights, that is, each of who might involve some bubbling up of these numbers, no more than log n steps, implies that this whole process takes n subtrees times log n bubblings up within each subtree, which means the whole process is n log n. Now, it turns out that if we have that basic building block, you can implement sort in this novel way. So we looked at merge sort, we looked at selection sort, and bubble sort, and so forth. Merge sort's running time was what? So it was n log n, and that was pretty cool because it was much improved, recall, even visually when we demoed it over those quadratic implementations. But there was a catch to merge sort, even though we didn't dwell on it. What was the price you pay for merge sort's speed? There's more memory, right? A promise that you actually need essentially twice as much memory to have an auxiliary array for all the merging. If you use heap sort, you actually don't need such extra memory because you can do everything using this tree structure. Now, 10 seconds. That clock is still giving me 10 seconds. What the implication here is that if you throw n elements into one of these binary trees, heapify it in n log n steps, the promise I'll leave you with today is that you can begin to pluck out each of the elements in sorted order in only an additional n log n steps. So with that teaser, we'll see you on Wednesday.